This is a lesson on power and energy use in the work and energy unit. Just to review some concepts because they will come up when you work with power and human energy use. How do we convert energy to mechanical things going on that's useful for us, right? Is state functions, thinking about states and energy state before something happens and after an initial and final. And that these are true for scalars and vectors. So energy falls under there. We have different forms of energy that we know of. There's forces that do work, and typically we'll be looking at non-conservative ones because the conservative ones fall under potential energy due to location. So we have potential energy due to location and kinetic energy due to motion, translational for linear motion, and non-conservative work. We'll keep track of those. And we also know this larger principle that mechanical energy is conserved. And remember, mechanical energy is kinetic energy plus potential energy. It's conserved if and only if this net work by the non-conservative forces equals 0. So we're keeping dibs on what's happening in our system from the initial to the final position, if there's any non-conservative work going on. And if there's not, we can know that the initial energy, mechanical energy, is equal to the final mechanical energy. So, as we have done with other quantities in physics, is we can look at the time rate of change of a quantity. And that's what power is. Power is the rate with respect to time at which work is done. So, that's how we get this equation, P equals W over delta T. This is not weight, this is work. Okay, work over time. It has the units joules per second. Remember, this is work is energy, which is joules. T is time. Watt came along, and the unit joule per unit time is joules per second is a watt. So when you see watt, think joule per second. The power of many motors or engines is expressed in horsepower. So we're going to do a car problem with horsepower in it. And horsepower can be converted to watts. Horsepower is power, right? Horsepower. So it is a power, but it's a different unit. And to convert it to watts, it's 746 watts. So we'll keep that in mind. I will highlight as we move forward before we solve problems that this is how we can introduce time into the idea of work and energy. Prior to this, the only way you really had to get at time was through kinematics, which is an initial velocity, a displacement, a final velocity, an acceleration, and time is in there. And so that was how you got at time. This equation makes it much more elegant because now we find work and energy. Those are really easy quantities for us to calculate now. We don't have to do a whole free body diagram. We don't have to do all that. We just calculate the work and energy and then divide by time, and then we have a factor of time. The example I picked out for us to work on first is a car with some horsepower. Here's the horsepower. All right. How long will it take a 1,100 kilogram car powered to a useful output of 35 horsepower? Cars are typically more than 35 horsepower, but how much you actually get out of the engine depends on many factors. So, to reach a speed of 35 miles per hour, neglecting friction. And I'm going to assume that V initial equals 0, and then that will be our V final. And I'm noticing units going on. And this is how they make this sort of material more difficult is, power equals work over time. That's not a difficult equation at all. But how you calculate these quantities and what units they're in can be complicated, and you're seeing that. We have horsepower miles per hour rather than meters per second. So I'm going to do some unit conversion. It says neglecting friction, so I'm going to keep that in mind. How long will it take? So I want time. So if I solve for time, I get T equals the work divided by the power. So I'll have to identify those terms. Okay, so let's do horsepower. The power is 35 horsepower. And then I'm going to remember that 1 horsepower is 746 watts. When I multiply that out, I get 26,110 watts. So that's how much energy is being supplied, how many joules per second being supplied by that car. Okay, so I have the power term, but when I go to find time, I want work. And what's the work here? How long will it take for it to speed up? So the work done here is going to be some sort of change in kinetic energy. And when I think about that, I'm going to have a 1/2 mv final squared minus a 1/2 v initial squared. That term is 0, so I would just calculate 1/2 mv final squared. My mass is in kilograms. I'm going to want my v final in meters per second, so let's do that. 35 miles. I'm going to put it over hours. I know that in 1 hour, there's 3,600 seconds. Another conversion factor, and this is one I looked up. You could have other ones in your mind that you already have memorized to do this without looking anything up, but I looked up that 1 mile, so miles go in the denominator in order to cancel them out. 1 mile is 1.60934 kilometers. So we have kilometers. I need to get to meters, so I have to say that 1 kilometer is 1,000 meters. And overall, when I cancel my units, there's a mile, hour. I'm left with seconds. And then the kilometers cancel out, and I'm left with meters. So overall, I get meters per second. So V final, I'm getting to be, when you run this through, 15.6464 meters per second. So that's that final speed. And then I could calculate the energy required in order to speed the car up that far. Okay, so it looks like I'm ready to plug numbers in. The work is 1/2 mv squared over the power, which is a number I know. 1/2 times 1100 times 15.6464 squared, 1/2 mv squared, divided by that 2,600 110 watts, joules per second. And notice that my units are going to work out. I'm going to get joules over joules per second, and overall that will give me seconds. And when I solve this, I get T equals 5.1569 seconds. A little over 5 seconds. So it sounds like you're not pressing on the accelerator super hard, right? It's taken 5 seconds, a little over 5 seconds to get to 35 miles per hour. So that is how you do that. The second part asks, how long will this acceleration take if the car also climbs 3-meter tall hill in the process? So it looks like the work done here by the engine, right? This is the work done by the engine, is going to not only cause some sort of change in kinetic energy, but also gives some final potential energy, right? It makes it go up the hill, some change in potential energy. So the work done by the engine is going to be the 1/2 mv final squared plus mgh, that additional energy needed to make it go up a hill. So when I plug this all into the calculator, 1/2 times 1100 times 15.6464 squared, quantity squared, plus 1100 times 9.8 times this 3 meters I went up on the hill. Divide that by the power output of the car. And when you solve this, put in the right numbers and solve this, you get the time. Of course, is going to be a little bit more because there's more energy to be supplied. It's going to take longer, right? 6.3955 seconds. Okay. So now we can relate these things that we're doing with energy, kinetic energy, potential energy, work done by engines, etc., to a time because of the time rate of change. Power is pretty good. Also, we will be retaining this concept as we move towards other types of energy and remembering that it's an energy over a time, right? The units of power is joules per second. Keep that in mind as you move forward into further courses in physics. This is a common concept for energy output. The sun is measured that way, right? Electrical power plants, right? How much per second? What is the rate per second? The next topic I have deals with human energy use. How is this useful for us? So, a topic you may see frequently, which I'm presenting, is the human body converting chemical energy to mechanical energy, right? We walk around, we lift things, we digest, etc. So there's a conversion factor known as the mechanical equivalent of heat, which is calories. And if you've worked in chemistry or biology, you may recognize this. Calories is equivalent to joules. It's an energy, right? This is energy. And 1 calorie is 4.186 joules. I'm going to note, like for human energy use, when you see a calorie, like on a grocery label, it has a big C calorie, and that's actually a kilocalorie, which is 1,000 little C calories. Little C calories are the SI version. What you see on grocery labels with the big C is kilocalories. So watch out for that if you're doing problems or you're thinking about calories. There's a factor of 1,000 in there to get from a big C calorie to a little C calorie. And little C calories are SI. I chose a problem for us that was sort of maybe applicable, maybe scary. The results and implications of this problem I'm not comfortable with, but we'll work through this problem and you'll see why in the end. How long can you climb stairs at a steady rate of 80 steps per minute on the 250 calories of energy in a candy bar? Okay, so I just randomly, I know most candy bars are between 200 and 300. So just imagine there's one with 250, and this is big C calories. Okay, so this is energy. This is the energy that has to be expended. And the energy that has to be expended is the work. So I'm going to say that this is the work done is 250 calories. How long? What is the time? So that's a time. I don't know T. And so I'm looking at this 80 steps per minute. I think if I wasn't sure that the 250 calories was the amount of work that needed to be done, I might have a hard time with that. We're going to say that the power is 80 steps per minute. And I'm saying that because it has the time in it, right? The units on it is per. And so that's how we think of that, is per unit time. And so that's why I'm converting this to a power. Okay. So we're given units that we're not expecting. And we saw that on the previous problem. They're going to introduce maybe some unit conversions in this material to make it more complicated. So I can convert this value to an energy. I know that 1 big C calorie is 1,000 little C calories. So big C and little c are different. They're definitely case sensitive here. And then I know that 1 calorie, 1 little C calorie is 4.186 joules. And I can convert this number to a number of joules. Okay, and this is one of the implications that I was having a little bit of issues with. Not that it's the wrong number, it's just that it's a really large number. Okay, when you eat a candy bar of 250 big C calories, that's how many joules it is. Okay, I'm really reconsidering my candy bar eating. Okay, time I don't know. Power, steps per minute. You know, it'd be really great if I could get this to joules per minute. That would be really great. Or joules per second. Joules per minute would be fine, because it seems like if I'm climbing stairs after a candy bar, I'm going to be climbing stairs for some minutes. So maybe we can think of this. For each step, for one step, there's some sort of gain in potential energy, right? I'm moving up in the gravitational field. There's some sort of gain in potential energy. So for each one step, I'm gaining mgh worth of energy, joules, right? And one thing we're going to have to decide is what's the height being gained in one step. I'll say that the height in one step, I did a little bit of research. The typical height for a step is 7 inches. And when you multiply that by 2.54 centimeters per inch and then convert it to meters, you get, actually, this is like 17.87, I think, centimeters, which I rounded to about 18 centimeters, which is 0.18 meters. So that will be the height for each step gained. We get this much potential energy gained, right? So all of this potential energy will be, all of this candy bar will be transferred into giving our body potential energy. And there's transfer of chemical energy into mechanical energy into this potential energy. Now we're at the top of a building, right? So let's put our equation together. And this is part A. We'll put our equation together. The time has to equal the work over the power, right? Right? Power equals work over time. We solve for time, we get work over power. So we're going to take that 1,446,500 joules and divide by the power, which I know will be 80 steps per minute. And then you can see that this will end up be joules per minute. So I have joules on top and joules per minute on the bottom. So 80 times the mass. Oh, well, we need a mass. This is U. Let's say the mass of U, and this is just a general, like, average number, 72 kilograms. Whoever you are, I'll say you're 72 kilograms. We need a 9.8, and then the height of each step is 18 centimeters. So that's our MGH term, and we do 80 of those per minute, and we will get a minute out of here. And when you run these through your calculator, you get 102.955 minutes, which is also the depressing number. I'm eating millions of joules, and I'm going to have to walk stairs for over 100 minutes to get rid of them. So that's how you use time or get time out of this equation. That's part A. It says, how many flights is this? Okay, so we don't have to do any more really physics with this stuff. We have 80 steps per minute. We have 80 steps per minute. And then we have 103 minutes. And then what else do we need to do? Steps. Oh, height per step, right? One step. There's 16 steps per flight, one flight. And so our steps cancel, our minutes cancel, and we're left with flights. So when you multiply all that through, it actually equals a even more depressing number, which is 514.9774 flights, which is a lot of flights to go over 100 minutes for the candy bar that I ate. So that's human energy use. Again, we're taking some sort of chemical energies, chemical potential energy, transferring it to a mechanical energy, which we can quantify in some way.